All right, let me welcome you here. Margaret and Sebastian, are we all good?
We're good.
Yes.
Okay, thank you. Well, let me welcome you to the UVIG webinar on the interconnection of wind and solar power plants to weak grids. I'm Mark Ahlstrom, President of the UVIG Board of Directors. The Utility Variable Generation Integration Group was actually established way back in 1989 and is now the leading source of expertise and discussion around the integration operation of wind, solar, and other technologies. As a nonprofit educational group, our mission is to accelerate the development and application of good engineering and operational practices for the evolving grid. We offer a wide range of resources at our website, uvig.org, and we also convene both technical workshops and meetings of our user groups and working groups throughout the year. If you find today's webinar to be interesting, I strongly encourage you to consider attending our meetings. Our next major fall technical meeting is coming up in October 10 to 12 in Nashville, and we'll also include a tutorial on NERC's latest work on essential reliability services, as well as a set of meetings of our working groups. So that's one of our large meetings of the year. For those of you who own and operate wind and solar power plants, you would also be very interested in our fall operations and maintenance user group meeting, which is happening on October 3 to 5 in Destin, Florida. You can find details on both of these meetings at the events area at uvig.org. The webinar today will address issues that can arise with when wind and solar power plants operate on weak parts of the AC transmission system. Wind and solar power plants use power electronic converters, also called inverters, for delivering their power to the transmission system. The webinar today will discuss factors that may occur when these plants are in very weak parts of the AC system, including things like the dynamic response of the systems following system disturbances and interactions between the plants and other power electronic-driven network assets, not just other wind and solar plants, but also things like high voltage DC links and fax devices that are in the vicinity. As we'll see, there are ways to screen potential connection points, use dynamic models to evaluate these, and when necessary, to mitigate these issues. We're very fortunate and honored today to have a leading expert on this topic. Sebastian Achilles is the Managing Director of Power Systems Planning and Operation at GE Energy Consulting. His team activities include converter, turbine, and plant-level control design of GE wind turbines related to grid performance. And his expertise also includes the configuration of converter and plant-level controls in complex wind generation applications. His team responsibilities also include grid studies associated with PV solar generation, thermal generation, and fax devices. At the international level, he has been the secretary of the SCR B4.62 working group on the connection of wind farms to weak AC networks, and he's the U.S. representative on the SCR B4 group. So as Sebastian presents this material, you can submit your questions to us using the Q&A box at the bottom right area of your screen. I'll be organizing those questions and presenting them to Sebastian after he presents his slides. We expect to run through the hour, and the webinar is being recorded and will be available to you afterwards as well, so you can review it and share it. With that, let me turn it over to Sebastian.
Hey, Mark, thank you. Thanks for the introduction. And also, we really appreciate this opportunity from UVIG to share a bit of our experiences on this subject. All right. So this is the outline. In an hour, we're not going to be able to get in detail in all of the subjects, but the idea is to...
Excuse me, Sebastian?
Yes?
You're breaking up a little bit on the phone here. Are you on a headset or?
Is this better?
I think that is better. Thank you.
Okay. So I was mentioning that this is the outline for this webinar. There are several bullets listed here. We're not going to be able to get into extreme detail in all of them, but the idea is to mention key subjects of these aspects. So initially, we're going to go over some key characteristics of wind and solar generation, the aspects that are relevant for their connection to weak AC networks. And the idea is to talk a little bit about system stability limitations. That is, when we connect a large amount of this type of renewable resources to a grid, what are the type of limits we start seeing? When do we run into problems to add more renewables, or where the existing transmission infrastructure is insufficient for the renewables that already exist? We're going to share a few examples of those stability limitations. Then we're going to list mitigations. There are a large number of mitigations that can be done for these problems. Some of them are longer term or more expensive, and some of them are shorter term and less expensive. So we're going to list them. Then the idea is to go over screening system strength. You see that this webinar has the wording weak grids in the title. So one of the challenges of these applications is to identify when a grid is weak for a particular plant or groups of plants. So we're going to talk about those methods. Then a short discussion about modeling considerations, stability models and EMT models, and what to consider there, and then a short summary of this. So speaking of wind and solar generation characteristics, most of the modern wind and solar projects have electrical systems that have power electronics interfacing with the grid. And in general, what we're going to be discussing today about includes the generation concepts that are listed here. So on the wind turbine side, here we show the doubly fed asynchronous machine, which is basically a machine that has the stator directly connected to the AC network, and the rotor is connected to the AC network through a converter, basically a conversion from AC to DC and DC to AC. So we're going to refer to this as a converter. The doubly fed asynchronous machine has a converter in the rotor circuit. And these are very common machine concepts in the industry today. Then also wind turbines with full converters. In that case, you have a generator that has a converter for the full power. That is, all the power that comes out of the generation passes through a converter before it gets connected to the AC network. And then similarly for PV solar, there will be a PV array that is connected to a DC system that will again get connected to the AC. But in a sense, all the power from the PV array will be coming out of a converter. So these three concepts have different levels of power conversion. Particularly, we may want to differentiate the doubly fed that only has partial conversion. However, from the point of view of what we're going to be discussing, these three types of generation have similar characteristics. In general, all these generators have fast active and reactive current controls. So these converters are called voltage source converters in the industry because they have a DC voltage. However, on the AC side, they typically have current controls. This is an important characteristic for the problem or the type of issues that we're going to discuss today. Then in order to control current, particularly if you want to control active and reactive current, you need to have a notion of where the grid voltage is. So you synchronize with respect to that voltage, and you inject an active or reactive current. So all these concepts also include some type of synchronization to the grid voltage. And in general, this type of concepts that we refer to as current-controlled power electronic sources require some level of grid strength to operate stably. What does that mean? So grid strength can be understood in several ways. In this particular case, we're talking about the strength of the voltage. If in a particular bus of the system I inject a current and the voltage in that bus is not significantly affected by the current that I'm injecting, that system is strong. It's a strong network. On the contrary, if the voltage of a bus is significantly affected by the current I'm injecting, then that bus is weak with respect to the level of current that I am injecting. So in today's presentation, then, we're going to be referring to this type of sources, And when we refer to grid strength, we're going to be referring to the strength of the voltage to the injection of current. Now, let's talk a little bit about stability, right? So let's assume we have, for example, a long transmission corridor. So a long transmission corridor will be associated with to a large impedance, so that system will tend to be weak. Right? The voltage at the end of that corridor will be sensitive to current injections. So assume we have a system like that. Typically what happens is that in systems like this, before you're able to completely utilize the thermal capability of your conductors in that line or that transmission corridor, you will find some other type of limitations that are typically stability limitations. So if we think about more conventional systems with synchronous generation, those stability limitations are associated with transient stability. Transient stability has to do with the machines losing synchronism to each other on both ends of the transmission corridor. Dynamic stability, that is related to electromechanical oscillations through the corridor. So that will be power oscillations through the corridor, or voltage stability. So these are the problems that the industry is accustomed to see in relation to conventional generation. In the case of power electronic sources, and I'm going to use the wording power electronic sources to refer to the sources that we just discussed in the previous page. The type of stability problems are different and manifest themselves differently. So one of the stability considerations that could limit the amount of power that can be transferred through a corridor are fast control stability. That would be the interaction between, could be the transmission system and power electronic sources like wind turbines, PVs, SVCs. So different power electronic sources that have fast controls could interact, and that interaction could result in trips. So you would have to limit the amount of power that you inject in the system to avoid those interactions. And then we're going to see an example of this. Then the other type is voltage stability. You will see that from comparing the right and the left of this, basically transient stability is typically not a significant concern for power electronic sources. Although sometimes we use transient stability tools or stability tools, we're typically trying to assess the voltage stability in that case. And then dynamic stability, which is associated with the exchange of energy between rotating masses connected in electrical systems. That's also now of concern in power electronics because the masses of these sources, in the case of wind turbines, the masses of the wind turbines are really decoupled from the operation of the grid to a large extent. So when it comes to stability, then this type of sources have stability issues, system stability issues, and they manifest themselves different than with conventional generation. So let's look at an example of fast control stability issues. So this diagram here is just an example. Here we have 3 wind plants that connect to a high voltage system. This line is relatively long, and that gets to the substation where you have 2 outgoings. In this substation, we have an SVC. So in this system, there are several fast controls. We have the fast controls of each of the wind plants, particularly the converters in the wind plants, and we also have the fast controls of the SVC. So in this particular case, we have a system that is semi-weak, and here we have a fault in one line. We have to open the line, and we're left with a system that is extremely weak. When that happens, we have an interaction between the fast regulators, between the wind turbines and the SVC in this case. So you can see this is the black line is active power, and the red line is reactive power. So you can see relatively fast oscillations. These oscillations would typically be somewhere between 10 to 20 hertz. And have to do with this inner current control loops, or occasionally could be related to fast voltage control loops. That interaction it doesn't, I don't mean to say that you always have this type of problems with SVCs, or you always have this type of problems with wind turbines, but it's something that could happen. In this particular case, it was possible to resolve the problem by what you see on the right is the same contingency now with a different configuration of the wind turbines, more specific to low system strength operation. So these oscillations in this case could be solved by modifying the settings. The important observation here is that if you would have the same SVC and the same wind plants connected to a stronger grid, you don't see this type of interactions. So this is really a system phenomenon in the sense that depends on the different controls, and also depends on how strong the system is. The weaker the system is, the more likely to have an interaction between the different power electronics connected to the same network. Now, let's look at an example related to voltage stability. So in this case, there is no SVC. It's a system that has several wind plants, and it's connected through a very long transmission line. Most of the impedance is related to this long transmission line. And in this case, what happens is the system where this line connects to also has a fault and one of the lines is tripped, resulting in a system that is even weaker than originally. I'm going to use the wording sending end and receiving end to refer to the different quantities here in the next slide. So then here we don't have an SVC. We have several wind plants, and we're going to look at the voltage stability challenge. So on the left here, we have some field recordings. On the right, some simulations. I would refer to the field recordings because those kind of show a concrete stability issue that then was resolved. So what you see here are on the upper plot, you see voltages, and you will see the pink one is related to the standing end, so where the wind plants are connected, and the dark blue is the receiving end. So these are has the active power also on both ends. So you can see initially the voltages were close to 1 per unit, close to nominal, and the active power was close to the maximum power that you can get out of these wind plants. During a fault occurs, so the fault that is then cleared. During the fault, you see this behavior where the standing end voltage tends to go down quite a bit. This is as a consequence of the fault. This that looks as an oscillation. It's not really an oscillation. It's the effect of the negative sequence in these RMS calculations. So an important aspect of the fault time is that during the fault, the voltage was low. The wind turbines, in this case, saw the low voltage, and as a consequence of that, they reduced the active power. Right? That's a control action. When the voltage is low, the turbines tend to reduce the active power. And this is to help stability during the fault. At the time the fault is clear, the system recovers well. The voltage comes back to nominal and a bit higher because the active power is relatively low, so the voltage gets a bit higher. And after a transient around 250 milliseconds in this time scale, we see that the power starts recovering. That is, the wind turbines in this case start ramping up the active power to go back to where they were initially. And you can see here how the active power kind of goes back to the initial value. Now, in that exercise of increasing the power, we see that the voltage is coming down. And in fact, what happens is it ends up collapsing. So the increase in active power results in a decrease in voltage that ends collapsing the system. This is voltage stability in this environment with renewables. What are the characteristics of this? Well, there are many things here that are similar to the same voltage stability that has been studied in power systems for so many years. This is basically, we were trying to push more power. We were trying to push power, and we didn't have enough reactive power available to sustain that power transfer in this case. The characteristic of wind turbines is that the power pickup occurs in 200, 300 milliseconds. So the voltage collapse also occurs in 200, 300 milliseconds. That's a characteristic of voltage collapse with renewables. If they happen, they tend to be somewhat faster than maybe what we are accustomed to see in power systems 10 years ago. In this case, it was possible to modify the wind turbine voltage controls and the plant level controls, and also the plant level controls, basically coordinated plant level controls, to facilitate more reactive power during the power pickup, and that resolved the problem. This is a simulation showing the improvements, but the system has been operating for many years. I think I captured this, yes. So, and generally speaking, I should say that in both of the examples I provided, it was possible to modify the controls to solve the problems. There is a limit to system stability, and it's not that all the problems can be solved with converter tricks. In this particular cases, that was possible. So what are the mitigations? So there are a large number of things that can be done to increase the system strength. So in principle, the mitigations would include transmission upgrades like adding a line. Obviously, that's typically not desired, but in principle, if you add lines in parallel to the corridor that already exists, you will tend to increase the system strength. Trying to avoid radial systems so that single contingencies or that tend to be radial so that the impact of single contingencies is less severe in the system strength. Using series compensation tends to counteract the effect of the line inductances, and by doing that, you're basically also making the voltages stronger. You're increasing the system strength. Other elements that can be used to improve the system strength are synchronous condensers. Those have the advantage of increasing the short circuit level and also provide dynamic bars. Then some people in the industry also use SVCs and STATCOMs. These two have the advantage that they provide dynamic bars, and then you have to be careful that you don't have control interactions. But in principle, those could be used to, these devices could be used to mitigate some of the problems. Other options are special protection schemes. If there is a particular N-1 or N-1-1 contingency that is of concern, maybe you could have a special protection scheme, but that specifically operates in that case to resolve some of these issues. And then so these are maybe the more expensive solutions. In some cases, you have to go to that. Ideally, you would use the control features in the power electronic sources. In general, I would say that in the last years, we've seen significant improvements in the performance and in the availability of features of power electronic sources for low system strength. And then also power plant coordination. So some of the examples that we talked about were related to availability of reactive power after a fault is clear. So it's quite usual that this low system strength conditions are met when you have a large number of wind plants next to each other, maybe 5, maybe even more. So coordinating the plant level controls of all these plants enables a better use of the available reactive power and can help mitigate some of the issues related to weak grids. Now, how strong are grid conditions? And the industry has been dealing with system strength with HVDC for quite some time, and the experience from that is very useful. So what I'm showing here is an index that's called short circuit ratio. That is basically the ratio of the short circuit level measured in MVA at the converter divided by the megawatts of the converter. This is a very simple index to calculate. In general, the higher the short circuit ratio, means the higher the short circuit power, the more stable the system is. Now, a few comments related to this. The name short circuit ratio tends to be confusing because although it's a short circuit ratio, we're not really trying to understand a short circuit operating condition. We're basically trying to understand how strong the system is, like what is the impedance seen from the converter I'm connecting. So we shouldn't get confused with the name. This is not related to a short circuit operating condition. We use a short circuit tool maybe to calculate it, but this is not related to a short circuit operation. And then a very important characteristic of this index is that it considers a single inverter. So in this equation, I basically have a single location of a converter and I calculate the short circuit MVA at that location. So let's see how this applies to wind plants. So this is a typical setup. I have 3 wind plants connected to a transmission network. And let's say I want to understand if there is a risk of the type of interactions or voltage stability that we talked about before. Well, one of the first challenges that we have is that here we don't have a single converter, we have many. And in general, the interaction with manufacturers, I'm going to elaborate on that later, allows you to maybe consider like a single plant could be treated like a single entity. But still, you have more than one plant very often. So the use of SCR, so the short circuit ratio, is kind of complicated here because we cannot exactly do the same thing. And if we try to apply the short circuit ratio to each of the plants individually, like I'm going to calculate short circuit for this plant and I'm going to ignore the other plants, that's going to lead to optimistic results. So I'm going to have the impression that I can connect more renewables, or I'm going to have the impression that the risk is lower than what it actually is. So somehow characterizing the system strength seen by all these converters is of interest. And somehow we need to extend the short circuit ratio method to that effect. There are a few methods available in the industry for this. There is no agreement in the industry on which one to use for renewables. I'm going to describe 2 that I think are quite used in North America. The weighted short circuit ratio has been used in some of the ERCOT planning studies, and after that has been adopted by several in the industry. This method basically assumes no contribution from wind and solar converters. That is, we're going to calculate some short circuit levels, but we're going to assume that the wind and solar converters do not provide short circuit current to these calculations. This method will calculate basically a single value for all the plants. So let's say I have 3 plants. When I calculate the weighted short circuit ratio, I'm going to obtain a single number that represents all the plants. And then you would typically calculate this for the weakest conditions because that's what you're concerned about. You're not concerned about the highest short circuit conditions. So you would tend to calculate this for low load conditions and probably contingency conditions. And this tool can be calculated using a standard short circuit tool and some post-processing. This equation here can be understood as follows. This is the short circuit ratio I'm calculating, WSCR megawatts. That's the short circuit ratio. And here in the numerator, I have the summation of the short circuit MVA at each bus where I have a wind plant. So in this particular example, I will have 3 wind plants. So I will have short circuit MVA of the bus number 1 would probably be the short circuit level at this bus. And then I will have the short circuit level of the second plant at this bus. And then for the third plant could be at this bus over here. And then the value PR megawatts will be the megawatts installed in each one of those wind plants. Another method that is used is the composite short circuit ratio. This has been introduced by GE. In this case, we calculate a composite short circuit MVA level. Like we try to understand the short circuit level seen by all the plants at the same time. So this is the same example as the previous page. Now we interconnect the medium voltage buses of the different plants, and we apply a short circuit. When we calculate the short circuit, we're going to get an MVA. That's called the composite short circuit MVA. and we will divide that number by the sum of the ratings of the different plants. This will also give you a single number for all the plants, and it's also possible to calculate this using standard short circuit tools. So generally speaking, as you can probably see from this very simple description, to calculate a short circuit ratio, the mechanics to calculate it are relatively simple. You can use a short circuit tool, and you obtain these numbers, and you're actually describing phenomena that's quite complex. So it's a very simple index that describes complex phenomena. So there are limitations to this. So the advantage that this has is that it allows for a simple calculation that characterizes system strength, and you can do this early in a project. You don't need to have all the details defined in a project to estimate, to approximate or estimate system strength. It's an advantage of it. Some of the challenges of doing this is that in order to calculate this number, you need to know quite a bit about the grid. So you need to know the network parameters, not only inside of the wind plant, but also in the point of connection and way beyond that into the transmission system. And also you need to have an idea of the future projects, right? So we mentioned before that you need to consider the different plants that are going to get connected, not just one. So understanding that is a prerequisite to be able to estimate the short circuit ratios in a meaningful way. Now, let's say you go through this exercise and you get a number. You get this. During my contingency, during a low load condition, my short circuit ratio is this number. What do you do with it after that? So typically what will happen is that the manufacturer of the power electronic sources, particularly in relation to the inverter controls, may provide the short circuit ratio of reference. So what is the short circuit ratio that was considered in the design of the equipment? And if the short circuit ratio in the application is within what was considered in the design of the equipment, probably the manufacturer will state that there's an application that has a very low risk of instability. Now, if these indices are low or very low compared to the references provided by the manufacturer, then that will indicate that there is some risk of instability. Now, that doesn't mean that the system will not work. It basically means that there is a risk of instability. And normally what you would do is, for very low strength applications, you would do additional studies, more detailed studies, to understand if there are risks of trips, risk of control interactions, or risk of voltage instability. So again, you will calculate the short circuit ratio. You will probably have a dialogue with the manufacturer to understand how is the application compared to the design of the equipment and controls. And then if, based on that, some risks are identified, the next step is to do more detailed studies than the usual studies, let's say. Some modeling considerations. Generally speaking, in our industry, we talk about stability and electromagnetic transient models. Those are the two types of models. I think in general, the industry is inclined to use stability programs and stability models. It is a fact that the stability programs are associated with time steps and simplifications in the representation of the network that do not allow for the representation of all the details of the fast controls in the power electronic sources we are discussing. Now, that doesn't mean that the stability models are useless. It means that they have some limits of when they can be used. So in general, the stability models can be used to try to understand these problems up to a certain level of short circuit ratio. And what you may find is that manufacturers or the entity issuing a model will provide a a minimum value of your secret ratio where the model can really represent the equipment. So there will be a validation, could be a validation of the equipment behavior with respect to the models. And there will be a value below which the manufacturer may recommend to double check the results with a different type of tools. So it's about stability models. There is also an aspect that we're seeing more and more in the dialogue with stakeholders in the industry, and that's related to numerical issues. So as we start studying applications where the system strength is lower and lower, sometimes we see that when you try to run some of the simulations, the tools don't have a problem to converge numerically. It's very important not to confuse those two things, right? So there is a difference between numerical non-convergence and an equipment performance issue. So it could be that you have a simulation that cannot solve. That doesn't mean that the equipment has a problem. However, somehow we need to be able to analyze the systems. I don't mean to minimize that aspect, but I do want to differentiate between the two issues. Some manufacturers of equipment may provide models with enhanced numerical performance. I think we're seeing that more and more. We're doing that. I'm pretty sure others are doing that too. So we're looking into ways of having representations of the solar and wind turbines that allow for stable numerical solutions that you can concentrate on the actual physical issues and don't get distracted with numerical issues. But this is a problem that we see, and we also see this with generic models. Then the other type of models are the electromagnetic transient models, and I think in the industry we have some people that love them and some people that don't like them that much. Electromechanical transient models can include the details of relevant controls. So by this I mean they don't necessarily do, they can. So the type of simulations and representation of the network allows for the creation of models that replicate the details of the fast control loops. And these models can be used to assess the type of problems that we discussed. And there will be some cases where these models can assess the problems and the stability models may have some limitations. Now, the challenge with these models is that they are quite complex. So operating the models is quite complex. When you want to do simulations with many of these models in a network, it becomes even more sophisticated, more time-consuming. It is possible, but it requires different type of skills and tools. And also, these models tend to include proprietary information. And for that reason, manufacturers, if they have to provide models like this, they would do so by protecting their intellectual property. So these models will be provided in the form of black box, in the sense that you get a model that runs, but you don't see what is inside. So generally speaking, summarizing the modeling part, we see the industry now is basically using generic stability models. There are also manufacturer stability models that are more or less used in different systems. And then there are manufacturer EMT models. There is a trend to use generic stability models, and when there are issues, sometimes there are suggestions to jump to manufacturer EMT models. That is a possibility. We think that manufacturer stability models can be a good complement to generic stability models in many cases. Okay, final slide so that we leave enough time for Q&A. So generally speaking, the connection of wind and solar generation with power electronic interfaces is subject to stability limits. This is not different than what happens with synchronous machines. When you start combining long transmission systems with generation, at some point you have interactions limits. Those interactions are different with the power electronic sources than it is with a synchronous machine directly connected. The modern technologies include control features that have really evolved in this sense during the last years. in this facilitates connecting generation without having to build or add infrastructure to the applications. This can, however, not solve all the problems. At some point, you may need to add wires. You may need to add additional reactive power sources. But in principle, that has been a significant help in reducing the costs of applications in the last few years. Another aspect I will highlight is that the early identification of risks or stability risks in a facility really facilitate the timely mitigation. So some of the solutions require quite a bit of time to work out. Even if it's to tune controllers, the systems are so complex that this takes time. If it's to add a synchronous condenser or a STATCOM, well, that takes time too. Early identification of the potential risk is very useful. And to that effect, we talk about this short circuit ratio, or basically identifying how weak the grid is. We mentioned that understanding how weak the grid is depends on several things and requires sort of collaboration within the system operator, planners, developers, and manufacturers. That collaboration has to do with the availability of data of the grid, availability of data of the present and future plants that will be installed, and then availability of what was the design criteria for the controllers that will be connected to the particular network. And then we talk about short circuit ratio estimations, considering all the plants. These estimations are a very reasonable initial step in such collaboration between the different stakeholders to resolve and early attend these potential challenges in the project. And that's the material I had. So, Mark, if you want, we can open up for questions.
Excellent, Sebastian. Thank you. First of all, let me apologize if there's some of you who are on the phone line and did not manage to get into the webinar. We were careful to increase our plan with our WebEx provider here because we had a great sign-up for this, but I've heard that some people were not able to get in for some reason. So we'll be contacting your associates if they couldn't get in, and we'll certainly make the recording available, and maybe if Sebastian is willing, we'll even redo this webinar given the high level of interest we've had in it at some point. We have a number of good questions here. Very nice job. Some compliments came into you as we speak. First of all, Sebastian, something that I've actually heard as well is, people are like trying to do short circuit SCR type screens. What's the typical range of the short circuit current, short circuit ratio rather, that you tend to see on weak systems that would cause you to have concern?
Yeah, and I think that's a fair question. I didn't share any numbers during the presentation. What you would tend to see is that maybe I'm kind of representing two sides here. One is GE as a manufacturer in a way, and then GE Energy Consulting as a consulting entity. You will tend to see that manufacturers are reluctant to share short circuit ratios in general because those get better with time. So the limitations of today are not the limitations of tomorrow. However, just generally addressing the question, I think that still has some differences between solar and wind. I think, generally speaking, wind manufacturers have been exposed a bit more to this problem than solar manufacturers to some extent, and wind technology tends to be a bit more tolerant than solar technology, and I'm speaking in general. I do imagine that there are specific exceptions to what I'm saying. So a short circuit ratio of 3 or more is kind of reasonable or high. In the solar industry, maybe 5 or more is high. The 3 is kind of borderline in some cases. Short circuit ratios between 3 and, say, 1.5 are challenging, and there you get into different technology that's different. The response depends so much on the controls that some technologies may do better with in this range. But let's say 3 to 1.5 is the range where things may be okay or not, depending on the technology. And then between 1.5 and 1 is really hard, and that may or may not work. And below 1, it gets extremely difficult because your cycle ratios below 1 are also associated, tend to be associated, depending on the system topology, to basically the inability to transfer the power. Right? If your cycle ratio is too low, it means that the reactance that you're trying to push the power through is just too large. So below 1, things kind of don't work. There are exceptions, depending on the topology and where loads are connected. But generally speaking, below 1 is challenging. Between 1.5 and 1 would require some heroics and some very good technology to get that to work. And between 3 and 1.5, you will find that those tend to be feasible, but it kind of will depend on what is getting connected. And about 3, things will be generally fine.
And are these usually at like an N-1 situation that you're calculating these, like you showed in examples, or are there variations in how you would, what scenario you would calculate?
Right. So in principle, let's say if you're N-1, you would typically have the conversation on the N-1, and you're trying to see if you will be able to operate in the N-1 because that will be the most critical condition. Just to elaborate, because I think that you just did a very important observation. If you do your analysis with the N-0, but then you have an N-1 that is much weaker, then your analysis is not looking at the worst case. You may have some conditions where you have problems that you're not identifying.
Okay. And we had a question here, and I think you addressed it in your previous answer, that we are seeing improvements in the technology. So like a GE turbine from today versus 5 years ago, you're designing and engineering to make it more tolerant of these weaker grid situations, I assume. Is that right?
Right. I mean, from the point of view of a manufacturer, there are more and more applications that are like this. So having your products able to stably operate, or even to operate without having to do heroics in terms of application engineering, it's a good investment. So GE in particular has been doing that. I don't think, I imagine others have been doing similar things. GE in particular has been devoting quite a bit of the new product development in the area of improving controls for stable operation in weak conditions.
I assume that one of the challenges you have, though, is that it's not just your GE wind plants that are in the weak part of the system, and you have to deal with multiple vendors and multiple types of inverters there. How do you deal with that sort of interaction between plants and between vendors? Right.
So yes, that is part of the problem, and that's a good part of the complexity we were talking about before. So the way the industry is dealing with this is by creating models that can be used in simulations to estimate what will happen in the field. It's important that the models that are used, so you basically have a model from manufacturer 1, a model from manufacturer 2 of their equipment, of different plants, and then you will combine those in a single simulation to see how they interact. Those models will have to include the relevant characteristics to try to assess this type of problems. But I think in general, that's the way of addressing that is by using simulations.
Okay. So you have to have some level of information from the other plants and other OEMs or cooperation in terms of how you're going to deal with this, though.
Yeah, absolutely. And in general, this is something that an OEM, let's say GE alone, cannot solve. The developer alone cannot solve, and the system operator or the transmission company cannot solve. It kind of requires inputs from everybody. If the system is not too weak, this is relatively simple. If the system is very, very weak, then the problem is more complex and requires more exchange of information among the different parties.
Okay, makes sense. Now, we've talked a lot about wind and solar plants here, but I assume that, like for battery energy storage systems that are also using these converters, that the situation would be similar. Have you seen cases where you have interaction between wind or solar plants and battery systems so far, or do you expect there would be differences?
I think some of the problems will be the same. There are some battery systems that are required to have performances that are different and are required to do like black starts or operate islanded. So those battery systems have a different type of controls. I mean, the complexity of the system is similar. We're probably not going to see exactly the same problem. But for most battery systems that are going to be current controlled, I think you're going to see similar issues. Yes, no question.
Pretty similar in terms of inverters being used. Yeah. Okay.
Correct.
What about high voltage DC? Where have you seen cases where you have HVDC terminals in the vicinity of the wind or solar plants, and how do you deal with that?
Right. Yeah, that's becoming more and more frequent. So the experience is that those can be made to work. There are risk of interactions, but in principle they can be made to work. The experience that we have that may be relevant in North America at this stage is that we've looked at projects where a significant amount of wind will get connected to the rectifier end of HVDC, even the standard, the LCC HVDC, which is the one that's typically used for bulk power. And we've seen that all the features that have been developed to get the wind turbines to operate stably in weak systems are very helpful when it comes to connecting a large amount of wind to a rectifier end of an HVDC. The reactive power, the fast reactive power control capabilities, and the active power reduction options that wind turbines have these days can be very effective in mitigating stability issues related to faults in the AC system on the other end of the HVDC or in the DC system. So overall, I think that there is very good compatibility. It is possible to operate those systems with short-circuit ratios quite low, very, very low, lower than the numbers I mentioned. If the wind turbines or the solar plants are connected on the rectifier end of the system, which is typically what is intended anyway, and if these converters have the features that are becoming more and more frequent in the industry.
And would that be the case like for offshore wind, where it's connected to an HVDC link, where it would have an SCR of less than 1 in some cases?
Right. Yeah,
okay.
that case, I should have addressed that differently. So I was not referring to a case like that. I was referring to a case where you have an AC network and a large HVDC close by. The case of the offshore systems are a bit different, because in that case, there is no AC network besides the main converter terminals. In that case, what happens is that the converter that is from the HVDC, the converter on the rectifier end, the one that is interfacing to the wind turbine, that behaves differently from the ones that we were discussing. That one doesn't behave like a current control power electronic source. It behaves more like a voltage source. And in that way, it keeps all the current control power electronic sources of the wind turbines stable. So that will be a different. The wind turbines are the same or are similar. The converter that is on the rectifier side is quite different in the way it's operated with respect to what we discussed today.
Okay. We have a question here from our friend David Jacobson in Manitoba, who knows a lot about HVDC. He asks, have you considered applying MIE SCR to wind and solar? And what happens if the plant provides some short-circuit current contribution, for example, 1.0 PU current?
Yeah, that's a great question. Yeah, the multi-feed SCR that has been proposed in SIGRE for HVDC can definitely be applied for this. The calculation is a bit more complex The indices like the CSCR or WSCR that I mentioned are very simple, and the intention of that is to get people in the industry that are not familiar with this type of problems to estimate something that can be used for discussions, to start a discussion. For entities that have experience with HVDC that can apply more sophisticated indices, I think that works. In particular, the multi-infeed SCR is a very reasonable index to apply. And the way you would use that SCR will be similar in the sense that at some point you have to have a dialogue with the manufacturers to understand how those SCR compare to the way the equipment is designed. So, yeah, that makes a lot of sense.
Okay. Let's talk just a bit more about mitigations, because you showed examples like with STATCOMs, but we also, often hear about whether we're going to need synchronous condensers in these weak areas, which have a number of advantages. But can you comment on alternative mitigation solutions and what you're seeing in that space?
Yeah. Well, I think we're seeing quite a bit of improvement in the converter controls. Mm-hmm. And you will see in the industry the application of STATCOMs and synchronous condensers. The synchronous condensers have the advantage that increase the short circuit level. So it requires it's less complex in a way. You apply the synchronous condenser, you already get you can easily estimate the improvement in short circuit level, and you don't have a risk of interactions. There are some manufacturers actually that prefer to use STATCOMs, and in that case, you have to deal with the potential interactions with the wind turbines and the STATCOMs, which is, can be resolved, but it's an additional complexity. I think those two are a comparison of engineering effort and simplicity. The synchronous condenser in many cases tends to be more effective in the sense that you need less MVA than you would do from the STATCOM. So the fact that the price per MVA may tend to favor one technology over the other. One of the important differences is that you may need a smaller synchronous condenser than a STATCOM for a particular application. But I think in general you're seeing, we're seeing synchronous condenser requests for wind plants, not necessarily from GE turbines, but GE is also providing synchronous condensers. We see several doing STATCOMs, and we see a lot of plants that don't need anything because the controls get much better.
We have a question here too about the use of RAS or special protection schemes relative to wind farms. Where there may be complex schemes implemented, where in cases where transmission infrastructure where there's just not enough capacity to support 100% generation of wind plants under all conditions. For example, it could send a run back to signal them to reduce their generation for 10 seconds or whatever, or trip it off under certain conditions or dispatches. Is that a viable approach? And is that something like you mentioned WindSCADA 200 or products like that? Are there ways of dealing with that? And is that a practical approach?
Yeah, in our experience, that would be ideal, but it doesn't work too well. So, but this is a challenge, and I really appreciate the question because I should probably have elaborated on this. Some of the phenomena we looked at, it's really fast, right? So things that are, if you look at the interactions, are things of tens of milliseconds. Yeah, if you look at the voltage collapse, some things of hundreds of milliseconds. So typically, to send a curtailment signal to reduce the power of a plant is too slow to avoid the problem. So what you could have is that you have a contingency. Based on the contingency, you instruct a plant level controller to curtail. But by the time that curtailment is actually effective, the plant already tripped or something else in the grid already tripped. In some cases, we've seen that even transfer trips with 100 to 200 milliseconds delays may be too slow. And here I should probably elaborate a bit more. We've seen cases where the short circuit ratio gets to extremely low levels, like 0.7. So you know it's just not possible to push the power of all the plant or plants through the system after a particular contingency. So you know you either have to trip the plant or part of the plant just to be able to get to something that is stable in steady state. So in conditions that are that extreme, as extreme as that, we've seen that sometimes the transfer trips are not fast enough. We have been able to further improve the controls to have some turbines that are able to react to things like this. So you have like a portion of the plant that is able to reaccommodate their output or potentially trip to keep some of the units stable. So I guess the general response to your question is that, yes, we've seen the need to do those things. Generally, we've seen that the curtailment as an initial action is maybe slow. It may be needed to have a curtailment signal after you do something to keep the system stable, but initially it's not enough. So transfer trips of faster power reductions at the plant or turbine level may be required.
Excellent. In the interest of time, let's close it up with one more question here. We actually have some participants here, like from Kenya, and asking about other small island systems. About, are there ways to incorporate wind and solar at the extremes of these extremely weak grid or island systems that would actually, help the voltage support and the adaptability of these systems? I mean, how would you deal with this on extremely weak or island systems?
Okay. Yeah. So the voltage support has different time frames, right? So wind turbines and wind plants have voltage support characteristics that are helpful and really can help keep the voltage in good levels within 100 milliseconds to 100 milliseconds or so. However, you still need to solve the problems that we discussed today. So when you have an islanded system and you want to use the type of solar and wind controls that are normally used in the industry, you will need something else, some other source that provides system strength. If you look at the offshore systems, that is a converter that operates like a voltage source. If you look at other systems, it could be a synchronous condenser. You will need something that provides system strength if you are using the standard products for PV and wind. You will need that to solve the problems we discussed today. In addition to that, you can use the wind turbines and the solar plants to provide reactive power. Some technology can provide very fast voltage control, and that can help sort of the steady state or slower phenomena. So sorry, I have a complicated response. Voltage support, wind turbines can help already. You still need to solve these issues that we described today about transitions after faults, and for that you do need something that provides system strength.
Very good. Well, it sounds like, as we often find these days, it's an exciting time to be an engineer in this space. You can find your way around these problems, but there's a lot to think about and a lot to work on these days. I want to thank Sebastian very much. We are recording this. We will be sending you an email with the recording in a few days as soon as we get that packaged up. Also have a question. If Sebastian is willing, we'd be happy to share a PDF of the presentation if you're okay with that, Sebastian.
Yes.
As well as, if I didn't get to your questions, I apologize. We had many questions here, but if you mail those into info@uvig.org, we will pass those along to Sebastian and try to get you additional answers as well. So I want to thank you very much. Thank you so much to our speaker, and We will be back in touch with details on this presentation. And again, I encourage you to check out uvig.org for additional information and upcoming events. Thank you very much.
Thanks, Mark.